In this video, I'm going to describe 3 different ways you can create a wake resolved region behind a wing. In this case, this is the ONERA M6 attached to fuselage. And so the first thing I'm going to do is actually examine this volume mesh so you can get an idea of what we're working with. So you can see that basically behind the wing, outside the boundary layer, these cells grow pretty rapidly, and we start to lose our ability to resolve that wake. And what we can do is there's actually a global block attribute called the boundary decay, but it's global in the sense that if we adjust that, if we increase that value as we approach 1.0, it's going to refine the entire mesh, all right? When really all we want to do is maybe locally refine downstream of the wing to help resolve those wake features as they move downstream. Okay, so that's what this is about. I'm going to go through 3 different ways of doing that. Now there's more than these 3, but these are the 3 ways that I've used in the past. Okay, so the first thing I'm going to talk about is an attached wake sheet. So I'm going to open up this and we'll zoom in here, and the first thing you'll notice is I have a structured trailing edge. Generally, this is what you will start with. When you have a finite trailing edge, you'll create a structured domain on that trailing edge, and the idea is that if you create a structured domain, you can diagonalize it, and by diagonalizing it, you get these nice right-angled triangles for use with T-Rex, which is our anisotropic tetrahedral extrusion tool, and it allows that boundary layer to wrap nicely around those 2 convex corners defining that trailing edge. Okay, but before we diagonalize it, we'd like to split that down the middle so we have a connector running down the center of that trailing edge, and we're going to actually have a wake sheet that attaches at the midpoint of that trailing edge. The first thing I want to do, though, is I want to take that structured domain and I want to split it away from the wall. Okay, so I'm going to split that, and the idea is that we're going to actually be growing boundary layer elements off of this wake sheet as well as the wall, and we don't want those to collide, so I've kind of separated that a little bit. And then I'll ensure I've actually got an odd number of points across the trailing edge so I can split it right down the middle. So I'm going to split that in the I direction, and by doing that I now have 2 halves and I have a connector running down the center that we can use to create our attached wake sheet. All right. But what I'm going to do first is I'm going to grab those structured domains and I'm going to go to create and diagonalize them. Again, triangulating those domains so we can present that to our T-Rex volume mesher. All right, so I'll grab that connector, and what I'm going to do is I'm going to translate that downstream. So we'll go edit, copy, paste, we'll do a translate. All right, I've already got my translation vector defined, but we'll start it over. So we'll pick this point, and we want that point to go 1 unit in the x direction downstream. Okay, so we'll zoom out here and you can see where it's at. All right, you can move that point basically wherever you want. So say we want it there, click OK. The next thing is I need to connect it. So basically what we're doing now is we're assembling an unstructured domain, which is pretty easy. So I'm just going to go and create that unstructured domain. So I'm just going to connect everything up. All right, and then I will dimension and assemble. So again, we're just creating an unstructured domain. It's attached to the trailing edge. You'll notice if we zoom in here, though, that those cells on that wake sheet are much larger than the cells on the trailing edge. And for those of you familiar with T-Rex, you kind of want those cells where 2 domains come together, you want those cells to be roughly the same size, and that's going to allow that extrusion to march out of that concave corner much easier. So the way to do that, the easiest way to do that, is let's just use 2D T-Rex on the surface, much like we've done on the upper and lower surface of the wing. So I'm going to grab that domain, and I'm going to go grid, T-Rex, we'll specify our parameters, set up the boundary conditions for the extrusion. Again, this is all stuff that is in the tutorial workbook or available online, so I'm just kind of going through it. And initialize. Okay, so if I zoom in here, now you can see that those two domains at that location have roughly the same cell size. And now we can actually invoke the volume mesher to march boundary layer elements out of this region. But the first thing I need to do is create my block. Okay, so I've created this attached wake sheet. All right, now what I'm going to do is I'm going to just select all the domains, assemble my unstructured block. You'll notice down here that one block was created, but one domain was unused. This domain was basically unused in that block. It's a baffle domain, meaning that there's two sides. So what we're essentially doing is we're going to add this domain to the block definition, and by doing that, we are essentially fixing those points in the volume. Okay, and by fixing those points in the volume, it's going to influence the volume mesher. And that's what's going to allow us to have control of the distribution downstream of the wing. All right, so I'm going to grab that block and go Edit, Add Face, select this, save it as a baffle face, and now you can see it's added to the block definition, and we can actually go into T-Rex, Grid T-Rex, and set up all of our T-Rex parameters. One thing to keep in mind, if you are using an infinitely thin sheet like this, you're going to want to leave full layers set to 0. Full layers in T-Rex affects the decimation and refinement as it's advancing points. Okay, so by setting it to 0, you're basically allowing T-Rex to create multiple normals on convex corners, and that's extremely important back here on all the edges, basically the edges of this domain. Those are 180-degree turns that T-Rex has to make, and so it's actually going to splay off multiple normals from that boundary and allow it to nicely wrap around that trailing edge. If you set full layers to anything greater than 0, it turns that off. Okay, so just something to keep in mind. If you want to use a sheet to resolve the wake, you're going to have to leave full layers to 0. Okay. All right, so I've actually already got a completed attached wake sheet. So I'll just turn on the cut so you can see exactly what it looks like. We'll turn off the view of the domains. And you can see basically what we have is we've grown these boundary layer elements off of the sheet downstream. And then you can see, if we zoom in here to the trailing edge, exactly what we have. Okay, so we've got the boundary layer elements marching off the upper surface, off the trailing edge, and off of the wake sheet. And you can see it's a little bit challenging to get out of that corner. Okay, we got a nice 45-degree normal coming out of there, but it's still a little bit difficult to get out of that corner. So typically what I'll recommend is if you want to use an attached wake sheet, the best time to use it is if you have a wing that has a sharp trailing edge. And a great example of that is in Chapter 11 of the tutorial workbook. From the help menu, you can access that tutorial workbook. And I'll pull up that grid right now. Okay, so here is an example from the tutorial workbook of a wing that has a sharp trailing edge and attached wake sheet. So if I grab that and we take a look at the volume, you can see the same idea, okay, where we've got that resolution downstream of the wing, and right up next to the trailing edge of the wing, you can see we've got the upper surface coming here, we've got the lower surface, and then the wake sheet coming off the trailing edge, and you can see exactly how smooth that is. And this is why I recommend, if you have a sharp trailing edge, it's really good to do just an attached wake sheet. You don't have those growth issues that you'd have in that concave corner of a finite trailing edge, and it just makes for an overall smoother grid. Okay. All right. So the next way, I'm just going to open up the original mesh. The next approach is to do a detached wake sheet. Okay. You're basically going to set it up very similar, except it's not going to be attached to the trailing edge at all. Okay. And what I like to do first, if I'm creating a detached wake sheet, is I will examine the completed volume mesh. So I'll take a cut through here and zoom into the trailing edge. And I'll take a look at that boundary layer growth. And I'll just make a note, I'll just measure that and make a note of how large that is, okay, that distance, okay. So it's about 0.01 units. Okay, and the idea is that through some of the workshops we participated in and these grids that we've created, we've found that this boundary layer growth, these really thick boundary layers that we're able to get off of the wing, actually does a very good job of resolving that wake in the immediate vicinity of the wing. Okay, but as you can see, once we get outside of that region, the cells start to grow rapidly. Again, we don't want to use that global parameter because it'll affect the density of the entire mesh. So what we'd like to do is create a wake sheet that's detached, but it's just outside the growth region of the boundary layer grid. Okay, so it's always nice to note how large that is. Okay, in this case I've measured that, and roughly the cell size in that region, and then we can use that information to create a domain that's basically detached from the trailing edge and embed it into the block in much the same way we did in the first example. And this is the method that I prefer for creating wake resolution. All right, so generally what I like to do, the easiest way to go about doing this is to just pick the lower connector, okay, the connector that's on the bottom of the trailing edge, and we'll split it at a grid point. Again, the idea is to split it kind of away from the fuselage, and grab that connector and copy it, paste it, and do a translate. In this case, we're going to just translate it just outside that boundary layer. So the offset vector will be 0.01 in the x direction. We'll zoom out here and you can see that location is, we looked at the volume mesh, that's just outside the boundary layer region of our viscous mesh. Click OK. And now we've got this connector. And then what I'd like to do is basically take that connector and copy and paste it, and give it a translation vector, in this case of 1 unit in the x direction. Basically very similar to what we did before. And you can actually take these and take them all the way to the far field if you wanted to. Okay. And then I would go and create the rest of that domain. So I create the rest of the connectors. Okay. And I'll just give them a dimension in this example, and create an unstructured domain. So basically all we're doing is we're creating an unstructured domain. Okay, and the idea is we don't need to use 2D T-Rex in this case if you don't want to. In fact, I recommend not. I would just leave them isotropic elements and get them the right size that you want for the resolution downstream that you need. And again, you've placed it right outside the extent of that boundary layer extrusion. And then what I would do is you have the block, okay, and you can just use that block and then add that wake sheet to the block definition just as we did before. So you'd select that wake sheet, you'd save the baffle face, and then you'd basically reinitialize your T-Rex volume, keeping in mind to ensure that the multiple normals feature is being used by setting full layers to 0. Okay, and I actually have the completed mesh, so I'll pull that up for the detached wake sheet. Okay, so if I zoom in here, you can see the detached wake sheet. It's just outside that extrusion, and you can see basically what it's done is it's fixed those points in the volume mesh. It's provided that resolution that we need. You can see we have that clustering downstream of the wing, and then we got the growth basically outside of that. Okay, so that's the method that I prefer for getting the resolution that I need downstream from a thin feature like a wing. All right. Now the last method, again, it's very similar, except we're using a box. So I'll just pull up the completed one. Generally what you'll do in this case is it's also detached, okay, so it's just outside the growth region of the wing boundary layer grid. And what I like to do is I like to create these boxes, these embedded boxes for bluff bodies, fuselage, a store, a car is another great example. And you can create these out of hex elements. You can create just a refined tet region by creating a block full of tets. You could create a prism block back there. And the idea is basically it's very similar to the detached wake sheet, except you're creating a block downstream of the wing. Okay, so I basically, in this example, created a hex block, and then you'd add it to the block definition just like we did before. So in this case, it's actually already a part of that. So it's add remove faces. I'm just going to remove it. So you'd have something like this. Okay, you come into this tool. Then what you would do is you would select the faces of this block, basically I've just picked one. I can click all adjacent and it'll pick the rest of them automatically for me. And then I would save that face and add it to the block definition. And what that basically does is it takes that big block and pokes a hole in it, and that hole is filled by the elements within that yellow block, in this case hex elements. Okay, so if we take a look at this, just grab both blocks and go look at the quality and turn off the view of the domains, and you can see exactly what we have here is we have a box downstream filled with hex elements, okay, downstream of the wing. And so this is another way that you can get the wake resolution that you need. Just build another block downstream, add it to the block definition, and then reinitialize. Okay. In this case, we don't need to turn on multiple normals because we actually have a fixed finite feature with finite. In this case, this edge right here, we can have a single normal coming off there. And in fact, in this case, we're not actually even growing these boundary layer elements off of this block. So it's not necessary to use multiple normals in this example. Okay. So those are just 3 ways of creating a wake resolved grid, either by using an attached wake sheet, which again I would recommend for features with sharp trailing edges, a detached wake sheet, or just embedding another block within your larger overall grid. Okay, so thank you very much.